Humbug Whistle? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
All right, hello and welcome to today's problem. All right, so we have in our problem we have two boxes. We'll call the smaller box M1 connected to a spring. Here's our nice squirrely little spring there. And M2 is going to be a larger box. And what's going to happen is this spring is going to be released, so it's going to push this first box to the left here, second box to the right. All right, so we're going to use several equations. We're going to define our numbers first, with the numbers we have. So M1 is equal to 11.2 kilograms. M2 is equal to 21.7 kilograms. Our spring constant K is equal to 1,330 newtons per meter. And it is compressed a distance of 0.141 meters. All right, here we go. So how I solved this problem, how I would like to solve this problem, is we know that the initial energy right here in the system right here is going to be all stored in the spring. And as the spring is released, it's going to give energy to each of these boxes, and it's going to be in the form of kinetic energy. So initially, we have some potential energy stored in the spring, and in the end, that is going to be equal to the kinetic energy of the first box plus the kinetic energy of the second box. So the equation for kinetic energy stored in the spring can be found using Hooke's law. It's half kx squared. So plugging in our values right here and here into this equation, we get 13.22 joules. All right, so that is our initial energy. Look, we're already a good ways through the problem here. Now we know that the kinetic energy, the equation for kinetic energy is equal to kinetic energy K is equal to half mv squared. All right, so plugging this into each of these spots right here, we're going to know that the initial energy is going to be equal to half the first mass times the first velocity squared plus half second mass times second velocity squared. All right, and at this point, we know this value right here. We know both of the masses, but we're missing both of the velocities, and we only have one equation here and two variables we're trying to solve for. So we need to find another equation. This other equation that we are going to be using is the equation for momentum. So momentum, I'll just write it out here. So often the letter P, it's mass times velocity. And momentum is pretty cool because it is always conserved. So that means that if this box starts flying out this way, right, and this box shoots out this way, the total momentum of the system will still be zero because that's the momentum it had when initially, right, before the spring was released. Because initially there was no velocity, right? So this equation goes to zero because v is zero. All right, so that means that using that equation, we know that m1 v1 is going to be equal to m2 v2. And this is if we're looking at just the magnitudes of each of these values. Of course, the velocities are going to be opposite in direction, right? So technically, we do have a minus sign right here. What we can do is we can solve for either v2 or v1. I'm going to solve for v1, but you can solve for either one, whichever one makes you happiest, I guess. So I'll write it over here. m1 v1 divided by m2 is going to be equal to v2. There we go. Now we have two equations and two variables, so we can solve, and that will make us nice and happy, and we'll be able to find v1. So we have the initial energy is equal to half m1 v1 squared plus half m2. Here's the exciting part right here. We're going to throw this equation right here in v2's place. So we have m1 v1 squared and m2 down here. All right, now we can get solving. So we're going to multiply both sides by 2. So 2e1, and I'm going to probably, let's see, let's simplify this first, I guess, before we get too crazy here. So this squared is going to be distributed to each of these. We can cancel out this m2 right here with one of the m2's right there. So we're going to get m2, 1 m2, and m1 squared, v1 squared right there. And we can continue on here solving for v1. So there's a v1 in both of these terms, so we can pull that out. v1 squared. And that's going to mean that this is going to all be m1. Oops, there's a plus sign right there. m1 squared. All right, I was just pulling the v1 squared out of both of these terms right here. On this side, we still have 2e initial. We can divide both sides by this and take the square root. So that's going to look pretty crazy here, but it's going to get better. Things always get a little worse before they get a little better, right? All right, so m1 squared divided by m2. All right, and here's the exciting part. We're going to take the square root of all of this. Whoa, that is all equal to v1. And if you plug all the numbers in there, you can take a moment to do that now if you don't trust me, or if you trust me, we are going to say that this is equal to 1.25 meters per second. So that's our velocity, right, for v1. So this box is going at 1.25 meters per second. Now we can solve for v2 using this equation right here, our handy dandy equation. So m1 v1 over m2 is going to be equal to v2. So if we plug in 11.2 kilograms, 21.7 kilograms, and 1.25 kilograms, we are going to get that v2 is going to be equal to 0.645 meters per second. And that is going to be the velocity of v2. And there you have it. Hope this was helpful, and good luck.